All right, we are covering 6-7, the last section that we're going to cover in Chapter 6, Graphs of Polynomial Functions. So we're going to analyze properties of n behavior to analyze, describe, and graph polynomial functions, and we're going to do some simplistic graphing basically using the roots of polynomial functions. All right, so polynomial functions are classified by their degree. We looked at that at the very beginning of this chapter. The graphs of polynomial functions are classified by the degree as well. So each graph is based on the degree and has a distinctive shape. And we kind of looked at that when we looked at multiplicity. If it has a certain number of roots, the shape of the graphs looks a little different. It's a very similar thing for graphs and n behavior. So here's the table that they give you. You can see here's a linear function, and which basically looks like a line, quadratic functions, cubic functions, quadratic degree 4, and quintic degree 5. So they tend to get more convoluted as the degree increases. Notice the number of times a graph changes behavior or direction is the degree minus 1. So for instance, of degree 1, it never changes direction. It's always going in the same direction. Degree 2, we're going this direction and then we turn and start going up. Here we're going up and then we go down and then we go up. So we change directions twice, and we're going to change directions 3 times, going down, change direction, change direction, change direction. So that's what that means. All right, so n behaviors describes the values of the function as x approaches infinity, both positive and negative. And we can define that behavior based on the degree and the leading coefficient of the polynomial function. So there's basically 4 different categories or cases that we're interested in. And I'm just going to show the whole graphic at once. All right, so if you remember when we talked about multiplicity, if there was a multiplicity of 3, we could look at the graph and see there was a squiggle. I call it a squiggle. If we had a multiplicity of 2, it would touch the x axis but not cross it, so we would have something that looks like that. If you remember that, that's going to be helpful here, because what this says, this is about the leading coefficient, which is the coefficient in front of the highest degree term. So if it's greater than 0, which means it's positive, then we're going to look at this row. If it's less than 0, which means the leading coefficient's negative, then we're going to be looking at this row. The columns have to do with the degree. So this is odd degree, which means 3, 5, 21, and this is even degree. So let's look at each one. So if the degree is odd and it's a positive leading coefficient, basically this looks just like a cubic function. You're going to get a graph with a squiggle. So the squiggle is going, it kind of goes downward to the left and upward to the right. And that's, if you can remember these 4 graphs, it's going to help you figure out the n behavior. So if it's odd and it has a positive coefficient, if degree is odd and it has positive coefficient, you can see the graph looks like this. And what does this say? It says as x goes toward infinity, that means as x is getting bigger, what's happening to the graph? The graph is going toward infinity. It's getting larger and larger. So the polynomial also goes to infinity. On the other hand, as x is going more and more negative, it goes toward negative infinity. The graph of the polynomial is also getting more and more negative. So the value is getting to be smaller and smaller, or more and more negative values of y. So the polynomial is also going toward negative infinity. If we have an even degree, so an even degree you can think of just a quadratic parabola graph. It looks like this. So as we're going toward negative infinity, and that's in this direction, what's happening to the graph? Well, Well, the graph is increasing in value. It's getting more and more positive. So actually, the polynomial or the graph is going toward positive infinity. And the same with this. As x is going toward positive infinity, the polynomial is also going toward positive infinity. So remembering the graphs is going to be the best way toward understanding or remembering the end behavior. All right, so what happens when the leading coefficient is negative? Well, you're basically flipping the graph. So on a cubic or on an odd number, odd degree graph, it's going to flip it from going in this direction to going in the opposite direction. It's kind of like a flip over the y-axis. So the squiggle is now reversed. And you can see as x is going toward negative infinity, the polynomial, oh, I'm sorry, so negative infinity is this way. So as x goes to negative infinity, what's happening to the polynomial? It's getting more and more positive. So the polynomial actually goes to positive infinity. However, when the x is going to positive infinity, the graph is actually going toward negative infinity. If we look at an even degree with a leading coefficient less than 0 or a negative leading coefficient, it basically flips the graph over the x-axis. So as x goes to negative infinity, the polynomial also goes to negative infinity. As x goes to positive infinity, the graph is still going toward negative infinity. So that summarizes the possible types of end behavior that we're expected to understand. So let's look at some examples. Identify leading coefficient, degree, and end behavior. So we're going to identify the leading coefficient and degree to help us figure out which end behavior that which case that we want to be working with. So here is our function. It's in standard form. Our leading coefficient is equal to -1. Our degree is going to be 4. So that means we have a less than 0 even. And if you remember, I remember that graph looks like this. So that means as x goes to negative infinity, p of x is also going to go to negative infinity. As x goes to positive infinity, p of x also goes to negative infinity. So either way, x is going to be p of x is going to be headed toward negative infinity. And that's what is summarized here. All right, next example. So it's in standard form. Our leading coefficient this time is 2. Degree is equal to 5. So we have a greater than 0, odd degree. I remember that graph looks like this squiggle. So as x goes to negative infinity, what's happening to my graph? It's going to negative infinity. However, as x goes to positive infinity, I see that my graph is also heading toward positive infinity. Whoops. Okay, so those are my examples. Whoops. You should try this one and see if you can get the right answer on that. All right, so now we're going to look and see if we can figure out things by looking at the graph. Identify whether the function graph has an odd or even degree and a positive or negative leading coefficient. So let's look at the first example. And we're going to look at the end behavior to help us figure this out. Okay, so if I look at it, I see as x is going to negative infinity, my p of x is going to positive infinity, and if x is going to positive infinity, my p of x is going to negative infinity. So which of my graphs that we looked at on the first would model that? Well, it's going to be the backward squiggle. And this means I have a negative leading coefficient, and it's of odd degree. So I'm trying to match the end behavior with one of the 4 graphs from the beginning of the presentation, and the only one that would match this type of behavior is this graph, which is negative leading coefficient, odd degree. So notice it looks quite a bit different, but what is the same is this part, and this part, the end behavior part. All right, number 2, let's look at this one. So here we have, as x goes to negative infinity, p of x is going to positive infinity, and as x goes to positive infinity, p of x goes to positive infinity. So which of the 4 graphs would model that? The only one that models that kind of behavior is this one, which means we have a positive leading coefficient and degree is even. Okay, so oops, here's the answer. Last thing we're going to do is graphing, and it's not it's not really complicated. You're going to find zeros. We've learned how to do that before, and you're going to graph those and then graph a few or find a few extra points. So this is the procedure. You want to factor the polynomial. Then you're going to find the zeros by setting all those factors to 0 and solving for x. You want to find a few extra points in between the zeros to figure out what's going on in between them, and define the end behavior so that you know that you're going in the right directions on the end, and then graph. So I'm going to go through one example. All right, so here's the polynomial. First we want to graph, so we can greatest common factor, we can factor an x out. And then we're going to end up with x times x plus x squared plus, let me get rid of all that. If we factor an x out, we have x times x squared plus 5x plus 6. And this, of course, factors into x plus 3, x minus 2. All right, so we factored it. We're going to set all those factors to 0. And when we solve for x, we end up with these zeros. So the first thing I'm going to do is actually graph those 3 points. So I have a 0 here, -2, and -3. So I need to know what's happening in between. So I'm going to find points in between. So first point I would try would be -1. Find out what's happening, what the value of x at -1 is. The easiest way to do that is to use the factored form. So when x is equal to -1, if I plug that in for x here, it's easier. Whoops. So that's going to give me, hold on, that's going to give me -1 times -1 plus 2 is 1, times -1 plus 3 is 2, and this is going to end up being -2. So I have a point at -1, -2, which is here. And then what's happening, I did similar things here for 4. When x is equal to 4, I have a point at -8. So that's going to give me -4, -8 is here. I did a point in between 3 and 2, which is 2.5. And you may not need to do all these points. You want to do enough so that you can tell what's happening with the graph in between the points. And so that's just barely above 0. And then my last point at 1 is at 12, so it's way up here. So we can guess, and it's not going to be exact because we don't have all the points in between, but you're just going to connect the dots at that point. And that's going to be my graph. So this may actually go way up here, or this may go way down here, but this is going to give us a good enough idea of the shape of the graph, and that's all we're actually going to be interested in. Okay, So here is one that you might want to try. See if you can do this. And then this is your homework. I'm going to have you graph these functions. They're not in the book, so you'll need to write these down to be able to do your homework. Bring any questions to class.